Welcome back to the Moldex3D Advanced Tips and Tricks. My name is Alex Baker, and today we're going to be going over sequential valve gating. In this lesson, we can learn more about importing lines versus generating lines in Moldex3D Studio. What is the actual purpose of sequential valve gates? And finally, applying valve gate timings in the process settings. Sequential valve gating is actually a very hot topic right now, and it's very underutilized in my completely biased opinion because a lot of the service quality defects that you see with hot runners and so on, things like weld lines or even things like sink marks, those can be mitigated with sequential valve gating most of the time. So let's take a short look at how sequential valve gating actually helps us, and then we'll actually get into Moldex3D Studio. We'll get our hands dirty with a little bit of interface and how to actually set up sequential valve gating in Moldex3D. All right. So what is sequential valve gating? So essentially what we're doing with sequential valve gating is we are going to, instead of injecting all the material through each of the gates starting at the beginning of the filling stage, we're actually going to turn on one valve gate. Once the melt front gets to the second gate, we're going to turn that one on, and so on. The main purpose of using a multi-gated part is to reduce the amount of pressure required to actually fill out the part. If I only had, for example, in this case, if I only had the one gate, I'd have to use this gate to push the material all the way along this flow path. You can almost think of these additional gates as almost like boosters for the material so that it's easier for the material to actually get along the flow path. Secondly, we're able to eliminate weld lines. So the weld lines, we're not injecting all of these gates at the same time, and therefore the melt fronts never have to meet one another. Because we're waiting until the melt front reaches this gate to turn on the second gate, and then the third gate, and then the fourth gate, we're actually able to eliminate the need for a meeting of melt fronts, which completely removes weld lines from the equation. Now you can actually see that through this little sprue pressure overlay. This is actually with our older interface, but you can actually see that the pressure requirement, and I just mentioned this a moment ago, the pressure requirement is actually not increasing even along the flow path. So you see that we get to a particular gate location, and then the pressure drops. And that pressure drop is because this valve gate is opening, allowing for an additional flow source. So this drastically reduces the amount of pressure required while also improving our service quality. And we can see that here. This is actually one of the common benchmarks that we like to show off for Moldex3D. I'm not going to get too much into this case study, but we were actually able to study how the valve gates were able to fix this sort of discoloration scenario, and more importantly, eliminate this weld line. So not only are valve gates able to really eliminate the weld lines from the equation, but actually the melt front coming out of the gates themselves, you can actually see these little valve gates opening up. This is another type of simulation we can run, which is a pin movement simulation. The how open or the stroke, how fast that pin moves down is actually going to impact the shear properties of the material and can actually lead to a discoloration if that material shears too much through the gate. So that's another type of simulation that we can run, but more importantly, with sequential valve gating, we kind of eliminate these sort of flow lines, or these really what they are is weld lines on the part. Now, some solutions with hot runners, you actually end up shortening your cycle time, not necessarily in the filling stage, because obviously if we didn't have sequential valve gating, the fill time would be shorter. But the fact that we are continuously flowing the material means that we're going to have a more uniform temperature distribution,
and that more uniform temperature distribution typically leads to a shorter cooling time. Also, because, and this is more of just because of it's multi-gated, not necessarily because it's sequentially gated, the shortened cycle time is going to happen because of the multi-sources for packing as well. And hot runners in general tend to have shorter cycle times than cold runners just because the pressure application is right at the part surface rather than at the top of a sprue or something like that. All right, like I mentioned before, we reduce the injection pressure and also the clamp tonnage. This is actually something that's overlooked quite often. Obviously, we just saw that the injection pressure was reduced quite a bit just because those valves opening ended up reducing the pressure due to a kind of just like an additional pressure source. But that pressure reduction also translates to clamping tonnage because clamping tonnage is really just a derivative of the injection pressure. All right, minimize the pressure loss. This is more of just due to the being a hot runner in general. The pressure loss change that we see from a cold runner to a hot runner is quite drastic because of the volume that we don't have to fill. All right, and then saving the material. This is just, again, hot runner. You don't have the cold runner. You don't have to fill any sort of volume. Skipping the runner removal operation. This just kind of shortens the production cycle. And then multi-cavity molds can be more easily facilitated with hot runners because of the lower pressure requirements and the lower amount of material required. Now, when we get into valve gate systems, so when I say a valve gate system, I mean that there's actually going to be a valve that's moving up and down in the hot runner to either open up, meaning that the material can flow through the gate, or close, meaning that the material can no longer move through the gate. And that kind of forces a gate freeze. So for those of you that might be more familiar with cold runners, you really have to wait until that gate freezes. Otherwise, your material will continue to shrink throughout the cooling process. So we want to make sure that in a cold runner scenario, we want to make sure that we're applying enough pressure to seal off those gates. But in valve gate systems, we actually just apply a direct pressure to the gate location on the part, and that essentially just removes the need for any sort of gate seal. You can still wait until the gate is frozen, obviously, but it's not really necessary because we're artificially shutting off the gate. And that whole process eliminates the possibility of gate vestige. So gate vestige is just material that's left over at the gate when the part is ejected. Other terms for this are drooling, and this type of valve gate system just eliminates that completely. So we can see eliminate drooling, prevent stringing. Those are basically the kind of in the same realm. You eliminate the weld lines, like I mentioned. The valve gate system, specifically with sequential valve gating, as we'll see over here, is allows us to eliminate the weld lines completely. So multi-cavity mold, same thing as the hot runner. Nothing too much more to mention there. And then sequential valve gating really just kind of puts the icing on the cake, allowing us to control when those valve gates, or when those valves open. So if all the valves were to open at the same time, we would possibly get more weld lines. But if we're able to more intellectually control the valve gate timings and look at the simulation from a flow balance perspective, look at how the material is actually flowing through the cavity, look at when the material actually gets to a particular region of the part, then we can actually start solving how we actually get through and control our sequential valve gatings to eliminate those weld lines completely. All right, so now let's go ahead and jump straight into Moldex3D Studio, and we're gonna import a model that is pretty conducive to valve gating. Really, when you're looking at sequential valve gating, most of the time it's either a very long part and a very thin part, or maybe you have a family mold, or maybe you have maybe you just want a more controlled flow front. So we're going to import a part into Studio that's a little bit more conducive to actually running that sort of valve gate simulation, the sequential valve gating simulation. All right, so setting up sequential valve gating is actually quite simplistic, especially if you're just a part designer trying to get an idea of how you can get this part to fill out. Even if you're a hot runner supplier, or even if you're a mold designer, you can get an idea of how you can fix weld line potential, or even going all the way out to the production stage. If you're seeing these weld lines, if you're using a hot runner system that has valves, usually those valves are tied to some sort of control system. So that control system can be utilized after the mold is made to more accurately control how the flow front moves through the mold. All right, so the first thing I'm going to do is create a project. Nothing too groundbreaking here. I'll just call it sequential valve gating. And press OK. We're going to use injection molding here, obviously. And then I'm going to go ahead and import the geometry called the sequential valve gating STP. All right, so this is a very long and thin part. Actually, the part thins out as it goes along. This was a fan blade, and and we actually had a lot of troubles with filling this part originally. We wanted to put the gate in the whole region here, but unfortunately, the melt front, or the pressure that we were applying to this point, was not enough to get the melt front to go all the way to the end of fill, and we ended up getting a huge short shot because the material froze off. Now, if we can apply multiple gates on this part, then we can actually get that material to fill out much more adequately. Now, we are always going to have problems with some sort of gate remnant. Using hot runners doesn't necessarily get rid of the gate location on the part. It just removes the amount of vestige that you see. So that's something to keep in mind, but we're going to treat this just like a normal injection molding, but with just multiple gates on the part. So what I'll ask you to do is, first of all, we're going to attribute this guy as the part. That is always the first step that we do. We don't have to worry about CAD Doctor here. I did fix this in CAD Doctor, but just to save a little bit of time, we're going to skip over that step. In all scenarios, in all regular scenarios, I would recommend, obviously, to go out to CAD Doctor, but in this case, we're just going to skip over that. All right, so now I'm going to look at the model thickness just to kind of confirm my beliefs that the material, or that this part actually thins out over the flow length. And I can take my scale down a little bit so that it increases the kind of the diversity of color. But we really do see that the part thins out as we move along our flow length. So what we're going to do is we're going to start our flow from the thick region. We always want to start from the thick region just because it's going to reduce the amount of initial pressure that we experience. Then once the material gets to the second region here, we're going to turn on a valve gate. And then once the material reaches the third region, we'll get a third gate turned on. All right, so I can either keep this shown or I can hide it by just simply clicking on model here. And I'm going to place 3 gates on my part, and very importantly, I'm just going to place pin gates. You could theoretically place any other gate if you want to, but I'm just going to use a pin gate in this situation because it will facilitate a certain type of simulation that we're going to discuss in a few moments. All right, the parting direction is going to be quite important here, so I'm going to make sure that my parting direction is correct, and in fact it is the Z direction, so we'll keep it default. And for a valve gate, any sort of valve gate simulation, you have to have the valve gates assigned as hot runners. The hot runner gate will allow us to control when the valve gates are actually turned on. All right, so I'm not going to be too specific with the placement of these gates. Obviously, I'm just kind of treating this as an initial run, or maybe just an initial look at the situation here, or at the flow progression. All right, so I'm going to place this first valve gate, and you'll actually see, first of all, you'll see the parameters of this gate. I can increase or decrease these if I so desire. I'm just more concerned with how the melt front is getting through this part. So if you think that the valve gate size is going to be a problem, then you can certainly reduce that by simply just changing the outlet diameter, which corresponds to the red dot here, red dot to red dot, and then green dot to green dot here. And the gate length is simply just the height of the gate. I'm just going to keep them defaults for now, but right underneath that, you actually see in the other parameters section, if you didn't check that hot runner gate box, you probably won't see this because this is specific to hot runners. So this valve gate control ID is going to allow us to control when the valve gate actually turns on. We're going to end up specifying that in the process, so we won't be doing it right at this moment, but we do need to specify the IDs for each of these valve gates. Obviously, I've only assigned one right now. I'm ultimately going to be assigning 3. I want to be able to assign those IDs ahead of time in the mesh so that in my process, I can use those IDs to accurately control the valve gates. Now there's a second one here called the hot runner controller ID. This would allow me to control the temperature. So whereas the valve gate control ID allows me to control the time, the hot runner controller ID allows me to control the temperature. We won't deal with that too much right now, so we're just going to look at the valve gate control ID. I'll click on the drop down and use edit number of valve gate controls. Ultimately, I'm going to have 3 different valve gates. So I'm going to enter 3 here, press OK, and then I'm going to assign this guy with a valve gate control ID of 1. All right, nothing too complicated there, but we do want to make sure that this valve gate control ID is set appropriately so that when we get into our process, our IDs show up, and then we're able to control each gate based on those ID specifications. So I'm going to press the green check mark here. And what's cool is it actually throws me back into this function and automatically checks hot runner gate. So I can just throw on my other 2 gates here. Yeah, I'm not placing them too specifically. I can modify these after I run my initial analysis. But I'll press the green check mark. And what I'm going to do is actually all of these gates are going to be assigned with the same attribution. So the 2 that I just created are going to have the same attribution as the first one. And when I say attribution, I just mean the properties of that gate, including the valve gate ID. We can confirm this by going over to display and check the valve gate ID. So this big section here, ID, it's right in the middle. We're going to click the valve gate ID. And we can see that the valve gate ID over here is set to 1, and we know that because these 2 were copies of this one, all 3 of these should automatically be set to 1. Once I select the gates, I'm going to right-click, edit injection molding attribute, and we'll actually see that when we come in here, it actually is not specified, and the reason for that is because Moldex3D knows that the valve gate ID here was set as 1, and these were copies of that, but Moldex3D knows that these still probably, being that we went into the attribute wizard, Moldex3D knows that we probably want to set these differently. So it just kind of takes away that specification, and I'm just going to set them appropriately. So first of all, I'm going to set both of them as 2. And then I'll set the third one with a valve gate ID as 3. So I'm just going to select that one individually. You see that this one's not selected anymore, and we'll change this one to valve gate ID of 3. All right, so now we see valve gate 1, valve gate 2, valve gate 3. That's going to make sure that when we get into our process, when we actually go to set this up, that our flow front is that we can control the sequential valve gate timings appropriately. Or I should say accurately, the way that we want to. All right, so I'm going to press the green check mark here. Again, nothing too groundbreaking. We've really just thrown our part into the modeling. We've given 3 gates, and then when we've assigned those as hot runners with a valve gate control ID separate from one another. All right, and if I'm just looking at the flow front, which in sequential valve gating, that's typically what you're going to end up doing. If I'm just running a preliminary analysis, I really don't need any sort of cooling system around this. The only thing left that I need to do is make sure that Moldex3D knows where to start from. So each of these gates will have to have what's called a melt entrance, which is just going to be simply a point on top of these gates that will kind of spread to the top surface. So I'm just going to go up to my runner system section in the top ribbon here. I'm going to click melt entrance, and that'll just pop 3 red arrows on the tops of these gates. So it'll just tell Moldex3D where to start from, and we'll be specifying when the melt front will start using the valve gate IDs here. But each of these gates have to have a starting point. Now, one common question I get about valve gate controls and how we can input these valve gate controls, one of the most important questions is, can I do this with a CAD geometry? And unfortunately, the answer to that question is no. The reason being that geometry runners will come in as one solid object, and because of that, there's no way to separate the individual timings of the valve gates. So if I have a geometry hot runner, or maybe if I get my step file of the hot runner system from the hot runner supplier, unfortunately, you aren't going to be able to control the timings that way. These need to be what we call a line-defined type gate. The line-defined type gate allows us to separate each of these valve gate IDs, whereas the CAD geometry would not allow us to do that. So important designation there. But we're just going to keep moving on through our meshing. The meshing for this part is actually quite simplistic. You could go through the Goldilocks method, and that's what I'm going to do right now. The Goldilocks method is kind of our current best practice for defining the size of our service mesh, and that'll just make sure that our computation time is reasonable while making sure that our part is well approximated. So I'm going to flip my part so that I'm looking down in the parting direction, in this case the z-axis. I'm going to zoom in my part so that it fills up the whole screen. That kind of normalizes the size of the part. We can see that this part is actually quite large. If I zoom it out so that it fills up this little scale down here, we can see that it's about 1/2 meter long. Pretty big part, but it doesn't actually matter as far as the node seating because we're going to normalize that by zooming it in so that it fills up the whole screen. I'm going to go to seating. Ask me to select the polysurface objects. I'll select my part and press the green check mark here. And then I'll click apply. And we'll see what the default node seating looks like. Usually we want about 2 to 3 nodes width of space. This little black node here will define the space between the nodes. So we want about 2 to 3 of these nodes to fit in the space between the nodes. So I'm going to decrease this value, let's say to 5 initially. Let's see what that looks like. It just essentially, we started at 10, we went to 5, so it essentially just doubled the number of nodes that we see on our part. And we see the spacing is still a little bit too much, so maybe I'll bump this down a little bit further. Let's go like 4. Getting closer, let's go 3. Yeah, that's about right. This is somewhere, maybe it's a little bit too fine, but we want to be able to have a reasonable distance between the nodes to decrease our computation time, but we don't want there to be so much space that the geometry isn't well approximated. So this will be a good node seating for us. You can go ahead and press the green check mark, sending you into manual node seating. We won't do anything with that here, so we'll press the green check mark once again, and that will finish out the function. All right, so I'm going to go ahead and generate the mesh here, and I'm just going to click generate and generate once again. That will allow me to boundary layer mesh for my part, and then it'll allow me to create the solid mesh for my gates. Now, very importantly, the mesh is going to be refined around the gates, and we'll see that as the runners are generated here. The mesh will refine around the gates to match perfectly to the part, and that's actually extremely important specifically for the sequential valve gating and really a hot runner analysis in general is that the melt front needs to be continuously computed from the runner geometry, or the runner volume here, I should say. It's not a geometry, it's just a line with the volumetric approximation based on that line. But you can actually see here that the mesh has refined around the gate to match perfectly with what's happening on the part. And all three of these gates have done that, and it maintains the 3 valve gate IDs. All right, once we're done with that, we can go ahead and press the final check button. Right, so final check just kind of shifting us from the modeling stage over into the simulation setup stage, making sure that we don't have anything obviously wrong. And our modeling in this case is quite simplistic. You can increase the complexity of this modeling as much as you want. You can introduce a cooling system if you want the warpage out of the simulation, and so on. But like I mentioned, we're just going to keep it nice and simple for a preliminary analysis. All right, selecting a material. So I'm just going to be using a simple polypropylene material. You can actually go through the material wizard. And we can go to Moldex3D bank. All right, I'll find my polypropylene materials. I'm just going to use the first material under polypropylene from A. Schulman. I'm just going to double click on this material. That will add it to my project, and there for my simulation you'll get this little prompt. You can press OK on this prompt, and then you can exit out of the material wizard, adding your material to your project. All right, so now I'm going to get into the process, and Moldex3D kind of creates a default process for us. But we're going to get really in depth into the process specifically for sequential valve gating, so that we can set this up to run. All right, first of all, I'm going to get into my what I call the classic mode of processing, and to do that, I'm going to go down to the bottom left corner where it says Option. We're going to change from simple mode, which might be the default for you, over to classic mode. So we'll make sure that we're in the classic mode of our process settings. Then I'm going to go over into the filling and packing settings. Sequential valve gating ultimately is a filling parameter. So we are going to go into the filling and packing settings, and then the valve gate controls are going to be down in the advanced setting section down here. So the valve gate settings are going to be, I guess, the processing of our sequential valve gatings is really what we've been leading up to this entire time. Going through the modeling, setting our valve gate control IDs allows us to control each of these gates separately. And you can see that I have 3 different gates here corresponding to my 3 different valve gate IDs, and you can still zoom in and zoom out if you forgot what your valve gate IDs were. Make sure that you have that checkbox under the display tab. Make sure you have that checkbox for valve gate checked so that you can see each of these gates. You want to make sure that before you run the simulation, you want to double check that your valve gate IDs correspond with the desired melt front that you set in the process. So the first thing that I'll point out here is the control point. This is the meat and potatoes of this function. The control point allows us to set the amount of statuses that are going to occur throughout the filling process for a particular gate. For example, in the default setting here, we have all 3 gates have 1 control point, and the action over here, we can see that the initial status is open. So what that means is that when the simulation starts, the valve gate is going to be open, and it will never close because there's nothing telling it to close. Now, if I increase the control point number, let's say I go to a control point of 2, now I have an initial status, and I also have a control. All right, so the control will tell us when to either open or close the gate based on the initial status. So for example, let's say theoretically, actually I'm going to do this for gate 2, because the first gate, typically the first gate we always want to be open. So the initial gate here, I'm always going to want this to be open. The second gate, I'm going to want to keep closed for a certain amount of time, and then I'm going to open that based on how the flow front actually moves throughout my part. So I'm going to increase, for the second gate, I'm going to increase the control point number to 2. And press enter. And we'll see that the initial status here is still open. I am going to change this because I don't want the initial status to be open. I want it to be closed initially, and then I want it to open at a specific moment during the simulation. Now, how this time is controlled is going to be based on the type, the controller type that you choose. So there's three popular timing controls that Moldex3D has to offer. There's timing, there's flow front, and then there's fill volume. There's 2 down here that are kind of like a VP switch timing and then a hot runner tip. These are kind of niche. The 3 up here are definitely more commonly utilized. So timing means that I can specify at a particular time during the filling process, I can say that this gate opens at this specific time. All right, so for example, let's say in this case my fill time is 1.7 seconds. Let's say that I want this gate to open up at 1 second. That means that I'm going to select my type as timing, and then I'm just going to come over here and change this to 1 second. So what this whole table here for the second valve gate, this valve gate 2, what this means is that initially our valve gate is going to be controlled as closed, and then at 1 second our valve gate is going to open. All right, so for the first second of our filling analysis, the gate is going to be closed, and then at 1 second, that valve gate will open, allowing flow through that volume. And then I can continue this on to our valve gate 3. I can increase my control point number. Say the initial status is closed. And then I control this to be maybe, I don't know, 1.3 or something like that, at some point after the second valve gate opens. All right, and that's usually the most common way to set up these valve gates, although there's a couple of other advanced techniques here. Now, when you're running an initial flow analysis like I have here, you might not actually know when that valve gate should open. So I don't know how long it takes to get from this gate to this gate as far as the flow front is concerned. So in that case, I might actually not want to control this by timing, but rather by flow front. So the flow front, instead of controlling by timing, there is going to be a little bit of timing over here. This is actually a little bit of a bug. You can ignore this when you're in the flow front control. What this means is that instead of controlling this valve gate by a specific time in the simulation, we're going to control it by location on the mesh. So I'm going to click select, and then I'm going to find a node somewhere on my part that's going to be close to our second gate here. So what this means now, you can actually see that the node number has been placed here. What this means now is that instead of controlling this by time, once the melt front gets to this node, once the velocity at this node becomes non-zero, this gate will open, allowing material to flow. And I can do the same thing down here. Flow front by node, select, and I can take a point just before this node. And the reason I'm going just before the third valve gate and the second valve gate is because it's going to take a small amount of time for the pressure to transfer from our melt entrance to the bottom of our gate. That actually happens in reality. And therefore, if I were to place this after, then the pressure will be delayed and there will be a little bit of a pressure spike. So to mitigate that, I usually want to turn on my valve gate slightly before the melt front actually reaches. All right, so the way I have it set up here is that the initial status is going to be closed, and once the melt front reaches this point, the valve gate will open, allowing flow. Now there's even one more state or another complexity that you can add, and that's to add one more control point. Typically, this will be done for the middle control valve or the middle sequential valve. And the reason for that is sometimes the material that's coming out of the previous gates is not impactful to the flow and therefore only increases the amount of pressure. This can be done, this is not necessarily always done. We always want to be applying some amount of pressure, but there are instances where you actually want to shut off that valve gate at a particular moment. And in that case, you can just increase or introduce a third control point saying that you want the initial status to be closed. Maybe I want the flow front to be by the same node here. Just choose that node. And then maybe I want the flow front to stop, or maybe I want this valve gate to turn off when the melt front reaches this point. All right, so you can see the valve or the mesh IDs are the same between these two. So once this valve gate opens, this valve gate, this valve gate closes. So that's another complexity that you can introduce to the simulation, which is kind of cool. All right, and that's actually it. That's as far as the valve gate controlling goes. There was one other that I didn't really mention too much, and that's fill volume. You can use fill volume very similar to the timing. If you look back at your simulations after you run your initial simulation, you can say that maybe once the part is half filled or once the part is 3/4 filled, we can turn on a particular gate. All right, but that's as far as the sequential valve gating really goes. And I'm going to press OK and then save to save my process. Obviously, there's a lot of other complexities to the process that I'm not going to get into now. But as far as the sequential valve gating process goes, or process setup goes, that's really it. So I'm going to save this new process file, and I'll close out of that process window so that we can go ahead and set up our analysis to run. We are actually going to run this simulation, and we can actually get the results extremely quickly for a sequential valve gating simulation because of a particular type of simulation that we have available. So to set that up, we're going to go to the analysis dropdown. And the default here is going to be a regular filling analysis. Obviously, when you're going to introduce more complexities to your model, maybe you even have an entire hot runner set up on top of this, then you will want to run a real filling analysis, and that will allow you to see all of the shear properties of the material and all that kind of stuff. But when I'm just running an initial analysis and I'm really evaluating how the flow pattern is moving throughout my part, trying to nail down my sequential valve gate timings, the quick flow analysis is going to be what you want to run. So instead of running the real filling analysis up here, we're going to run the FQ analysis or quick flow, which allows us to really ignore a lot of the material properties. And that's why I mentioned earlier that the material properties ultimately aren't going to be coming too much into play here for the initial analysis. Obviously, when we go to run our real analysis, we will want the actual material we're going to be using ultimately. But for this analysis, it's just going to be really considering how the melt front is moving through the part geometry. So this will allow us to nail down my timings and make sure that I have, if I'm going by seconds, then I can nail down that time exactly. Or if I'm going by node, I can see if that node is appropriate, or maybe if I need to pull back the melt or pull back this node a little bit. All right, not too much in the computation needs to be done, so I'm just going to go ahead and run this on the local computer, and it'll be quite fast, actually. So I'm going to go ahead and click run. Even though this part is over 1/2 meter long, the quick flow analysis is robust enough to kind of break down the simulation and only compute what is necessary for the simulation rather than everything like a real filling analysis would. All right, so we can see that the simulation is just finishing up here. This here, for anybody that's not familiar with the computing manager, maybe if you've used the older interface and had that annoying log window show up every time you ran the simulation, this computing manager is actually used for all simulations, and it allows us to kind of keep a log of where or when the simulations were ran. So if we maybe overwrite this with a second analysis, maybe if I run the quick flow analysis like I just did, I get my results and see that they're good. Maybe I want to run a real filling analysis then to see all of the different properties, things like your temperature, pressure, all of that stuff. We'll see with the quick flow analysis that the amount of results that you actually get are quite a bit reduced to pretty much just evaluating the melt front progression. You don't really get a whole lot else from the quick flow, but ultimately the progression of the melt front is going to be the main topic of discussion when we're looking at sequential valve gates, so that's perfectly fine. I should expect to see that the flow starts from here, and no flow should start from these two. Once I get to here, then I should see that this valve gate turns on, and then this valve gate should turn on after that. So you should see that in my results as the simulation finishes up here. All right, so it says my simulation is finished, so let's go ahead and take a look at the results. So to look at the results, I'm going to go back to my project tree, which is kind of at the top left corner of the screen underneath the new run button. There's a little toolbar here, and the first button in that toolbar is your project tree, which at the bottom has your results. All right, and right away you can actually see a pretty good premonition of what we're going to be seeing here. This is if all three of these turned on at the same time, I would see red rings like this at all three gates, and I do not, which is a very, very good sign. So what we're going to do is, instead of just looking at the colors here, although the colors are very pretty and maybe useful in some regards, we're actually more interested in the animation of this melt front. So to see that, I'm going to go over to the Result tab. You can also, under the Home tab, you can also click the Result button here if you so desire. It'll do exactly the same thing. I'm going to go to the Animation section of this ribbon here. And I'm simply just going to press play. And we actually see right away that my melt front just starts from this gate. These two gates are not open right away. So they are actually delayed. And we can actually see that, let me pull this melt front back just a little bit. So we can see that this gate is now turned on. You can actually see the melt front actually boosting a little bit out here. Maybe I'd want to delay this a little bit. Maybe I want to get this node a little bit closer so that the melt front remains kind of even, but you'll see that as this melt front moves forward, that effect should even out eventually. And we see that. And then the third gate should turn on exactly as we would expect as well. So nothing too groundbreaking again, but using the melt front timing, instead of using melt front timing, when you're going through this and initially specifying a node to turn on the melt front, it can help you out a lot more so that you can obtain the actual time at which this valve gate opens. And I should be able to see that through my filling log file specifically. All right, so we see at the, I'm just going to go over to log and filling. That'll open up our filling log file here. I'm going to go down to where the computation starts, and you can see right above the computation table, it states that valve gate 1 is open, valve gate 2 is closed, valve gate 3 is closed. And that's exactly what we would expect because that's what we specified. Now down here, it says the valve gate 2 is open at this time. So what this means is, if I went back through this and I'm actually specifying my timings, usually your valve gates are not going to be tied to the geometry itself. Sometimes you can get like a PID controller that will allow you to, or maybe just linked to a pressure sensor or something like that, that will allow you to open the gate based on the pressure at a particular node. But most of the time, these valves are going to be tied to an an actuation, and that that actuator is going to be controlled by a timing, not necessarily by a particular location on the part. So if I'm trying to correlate this to a real molding process, then I would definitely want to make sure that I have this timing handy. And you can actually use this timing in your future simulations if you wanted to. But in any case, we should be able to get the timings of our valve gates and evaluate how the melt front is impacted based on these valve gate controls. We've ran a simulation just to see how these valve gates are going to impact our flow pattern, and we've talked a little bit about how valve gates are, or why valve gates are applied in real molding scenarios.
Thank you for watching the Moldex3D Advanced Tips and Tricks. Please don't forget to leave a like on the video if you enjoyed the content. If you'd like to suggest a future topic, feel free to let us know down in the comments. And finally, if you want to see more content like this in the future, don't forget to subscribe to our YouTube channel.